So let us continue with the next one over here. From here we see the next. Over here what we have been asked is to sketch the reinforcement details at the beam and column junction. The beam and the column junction, what exactly happens, okay, where the beam meets the column. Over here, to see it practically, the top reinforcement goes like this, the bottom reinforcement goes like this. So from the face of the column, observe the distance of the bent over here, the bent bar, not the bent up, sorry, the distance from here of the whole thing, this is taken as LD. So whatever anchorage is required, it is from here to here. That is the length which is required to be provided. Now this will be in tension because the beam, when it is connected to a column, the top of the beam over here at the junction will be in tension and the bottom will be in compression. So if LD is necessary over here, that LD would be from this particular point, the face like this, that will be the LD in compression. That's the one. So when we are looking at this, that's the face. So from here to here, that is the distance from here to here, is the LD in tension. Some bars have been provided as horizontal U type bars. Now the LD in tension is this distance from here to here. The LD in tension has to be provided over there. Okay, so that's the typical detail of a beam column junction at a exterior column. Now this comes from the SP34. This is directly taken from SP34. Now in SP34 we get another one, the fixed end joint in a column, how the fixed end joint behaves. So if you see over here, this reinforcement continues further, the development length starts from here and goes on up to here. Okay, so that is what is important. And for a fixed end joint in a column, there are U type of bars which are provided over here. Okay, and see that the bottom reinforcement continues like this further. So that's the way we provide, or we give the detailing of the beam column junction. Coming to another problem, the next problem is calculate the development length LD for the following in terms of diameter of steel reinforcement in compression. Now in this case what we have been told is the steel is in compression. Now the type of concrete is M25, M30, M35, and the type of steel is Fe415 and Fe500. So the development length of the reinforcement is given by the clause in the IS code IS 4562,000, clause 26.2.1, page number 42. LD is equal to phi into sigma s upon 4 tau BD, where phi is the nominal diameter of the bar, sigma s is the stress developed in the bar at the designed load, and 4 tau BD is the design bond stress. So over here in this problem we have been told not to substitute the diameter of the bar so that the diameter can be put in later. Now let us have a look at that. The value of sigma s will be equal to 0.87 Fy, and tau BD is the design bond stress as per clause 26.2.1.1, page 43. The table has been reproduced over here. So for M25 and Fe415, the development length LD is calculated by phi into sigma s upon 4 tau BD. Phi we are not substituting. Now sigma s is 0.87 Fy, so 0.87, and Fy is 415 upon 4 into tau BD. Now in order to find this tau BD, I look at the grade of concrete. M25 gives me the grade of concrete as the bond stress as 1.4. Having known that bond stress is 1.4, please remember, if the bar is a plain and rounded bar, that is if the steel is Fe250, then we have to directly take the value as 1.4 itself. Whatever value is given, we have to directly take that value itself. Now if the steel is anything like 415, 500, 550 and so on, which are all high yield strength deformed bars, HYSD bars. For HYSD bars, the value of the bond stress gets enhanced, gets increased by 60%. So what happens is the value which we have got for M25 as 1.4, it is increased by 60% by multiplying 1.6. Now since these bars are in compression, the further increase in the bond stress is permitted. By how much? It is permitted by 25%. So whatever is there, we are increasing by 25% by multiplying 1.25. So the tau BD value becomes equal to 1.60 into 1.25 into 1.4. So tau BD comes equal to 2.80 Newton per mm square. That value is substituted over here. We get the value of the development length as 32.24 into the diameter. Now coming to further part, M25 and 500, since it is M25, since the bars are in compression, since the bars are HYSD bars, the high yield strength deformed bars, this calculation remains the same. Tau BD becomes equal to 1.60 into 1.25 into 1.40, which we have got from here, that is 2.80, that is substituted over here. The development length LD is equal to 38.84 times the diameter. So this is the way we calculate. Let us have the look at the other one. For M30 and Fe415, for M30 we have it as 1.5 over here. The design bond stress is 1.5. So if it is 1.5, since we have HYSD bar, the value is increased by 60%, and since the bar is in compression, it is increased by 25%. So we get tau BD equal to 3.00 Newton per mm square. Substituting that over here, we get the development length LD equal to 30.08 times 5. Similarly, for M30 and Fe500, it is equal to 5 into 0.87 Fy divided by tau BD. Now tau BD for M30 we have got it as 3.00 Newton per mm square. Substituting that, we get the value of development length equal to 36.25 into the diameter. Coming to the third part, that is M35 and Fe500. There is a typographical error over here. This is M35 and Fe500. So for M35, the value is 1.7. It is increased by, I think there is some mistake over here. This is not 2.72. There is a mistake. It is increased by 1.6. Okay, so 1.7 is multiplied by 1.6 and 1.25, and the answer appears over here as 3.40, which has been taken here. Okay, it is not 2.72, so it is 1.60 into 1.25 into 1.7. The answer is 3.40, which has been taken over here. So the development length LD is equal to 36.25 into the diameter. Similarly, for M35 and Fe415, the development length LD is equal to phi, the diameter of the bar, into 0.87 into Fy. Fy is 500, Fe 500. So there is an error over here also, typographical error. It is 500 here, into 4 divided by 4 into the value of tau BD is 3.4. So development length LD is equal to 26.55 into the diameter times mm. So much mm. So once we tabulate it, we get for M25 and Fe415, the value is, the development length is equal to 32.24 into 5. So suppose we are having the bar diameter as 10 mm, so multiplying 10 mm over here, for M25 and Fe415, we would get the answer as 322.4 mm. Similarly, for M30 and Fe415, it is 30.08 times the diameter. For M35, it is 26.555. For M25 and Fe500, it is 38.84 times the diameter. M30 and 500, it is 36.25 times diameter. And M35 and 500, it comes to 31.99 times the diameter. That's how we solve it. So whenever it is, the bar is in compression, and if it is a HYSD bar, we will have to increase it for the deformations. So increase permitted is 60%, and second increase would be because the bars are in compression, so another increase of 25% in the bond stress is permitted. So that's exactly how we solve this. Coming to the next one, sketch the reinforcement details for a cantilever beam projecting from a column. So the solution goes like this. There is a column over here. That's the column. That's the cantilever beam. So whatever is the steel required, we obviously understand that steel required over here at the free end is less, at the support the steel required is more. So you can understand over here two different layers of the bars are shown over here, but at the support the distance from the face to here should be equal to LD. Okay, that should be LD. Similarly, from the support till the portion where the bar is cut, the distance cannot be not less than greater of 0.5 times L, that is half of this, or LD. So this is the distance. Please note one thing which is very important. We find that the first stirrup starts at 50 mm from the face. Second thing to be noted is the steel which is provided down over here. It is 1/4 of the steel required in tension over here at the maximum point. So if the area of steel at the maximum point over here in tension is AST, then the steel provided for the compression portion is 1/4 of AST, and minimum 2 bars are to be provided. Another thing, please note, since this is positive moment reinforcement, it is considered to be positive moment reinforcement. It is taken inside the support by LD by 3. So all these things we have to take care of. Taking the next one, sketch the reinforcement details for a overhang of a continuous beam or a cantilever beam continuous over a column support. Now that's the column support. Cantilever beam projects out. Everything is the same, just like the previous one. Only thing is the projection, the development length will be continued in the straight line over here behind, in the behind beam. Rest everything is the same, providing this particular distance over here, which will be 0.5 L or equal to LD, whichever is greater. Down over here we are providing 1/4 of the steel which is required here, and this still continues in the support by a distance of LD by 3. So this is what we have to note. Now, having understood this, we come to the end of the chapter of shear and bond. Thank you very much.